Okay, it's almost time. 2 more minutes. While we wait for the other people, Michael, do you have any questions?
As of right now, I don't.
Okay.
I just read through the lecture notes for the last lecture, and I think I'm okay right now.
Okay, good.
Thank you.
Hi, David. Hi, Jason.
Morning.
Morning. Hello. 1 more minute, we can get started. Okay.
From New York, and we need an accountant from New Jersey. And
Okay. Noem, you like to turn on your video? Hi, Noem. How are you?
Hey, how you doing?
I'm good. Say, let me share my video then. I presume you can see my slides. Can you? Good. So today I'm going to talk about waves in layered media. This is a rather important topic. I'm going to talk about generalized reflection coefficient for layered medium. We have heard of the term generalized reflection coefficient for transmission line theory. So we would exploit knowledge from transmission line theory to understand generalized reflection coefficient. And then we do a number of physical interpretation things. The next topic that we like to study is the phase and group velocity, wave guidance in layered medium, and so on. So let's get started. So waves in layered media is actually a very important topic. It was first studied by Sommerfeld when he wanted to understand the propagation of radio wave over the good Earth. He was essentially interested in this topic, that if the Earth is layered, that if you have a radio station, and then if you send radio waves, he knows that above him there's an ionosphere. So how would waves propagate in a layered medium of the Earth and the ionosphere? And Sommerfeld did solve this problem around the turn of the century, I believe, about maybe 1901 or 1902. So we study this problem now. It has been regurgitated so many times so that we can actually use transmission line theory to help simplify the presentation of this problem. The problem on the top is the case when you send in a wave. This could be a plane wave. The plane waves get reflected and multiply reflected inside the layered medium and finally get transmitted. And we want to find this reflected wave at the top as well as the transmitted wave at the bottom. So you can reorient the top figure to look like this, where you send in the wave in this direction and then look for the reflected wave. I've taken this figure out of Kong's book, so the axes are slightly different in terms of labels. Usually I like to label this as a z-axis, not the x-axis. And this is another picture I took out of Kong's book, where he used a transmission line equivalence to show that this problem I have over here, okay, can be solved as a transmission line problem at the bottom. And I like to show you how, okay? So before we do that, let's use a blank slide to illustrate this. So we have shown that when you have a transmission line, especially multi-section transmission line, that if you have just a single junction transmission line, you can find the reflection coefficient gamma 1, 2, which is something like Z1. Maybe I can say that if this is Z01, this is Z02, it'll be Z01 minus Z02 over Z01 plus Z02. I believe that the minus sign should be here, because when I make Z02 equal to 0, I should get a negative reflection coefficient. We can say that this problem is homomorphic. Okay, we use the concept of homomorphism. That this actually is the same problem as this problem, that if you have a plane wave coming in and then a plane wave transmitted, the two problems can be made to be identical mathematically. Hence, you can also write down a reflection coefficient. For instance, for the TE case, that the reflection coefficient is mu 2 beta 1z minus mu 1 beta 2z over mu 2 beta 1z plus mu 1 beta 2z. Okay, and if you know the single interface reflection coefficient, we have seen that in transmission line theory, you can actually write down the reflection coefficient for, say, a multi-section transmission line. Okay, let me say that you can actually have as many sections as you like. You can actually even put a section here if you want. So if you know the local reflection coefficient gamma 1, 2, say this is 1, 2, 3, 4, and if you know the local reflection coefficient at this junction, then you can build up the generalized reflection coefficient, which says that gamma 1, 2 generalized at the 1, 2 junction is equal to the local reflection coefficient gamma 1, 2 plus gamma 2, 3. Gamma 2, 3 is generalized reflection coefficient at the second junction. So I would have something like 2j beta 2z L2. Let's assume that the second line has a length of L2. Okay, and then the denominator is 1 plus gamma 1, 2, gamma 2, 3 tilde e to the minus 2 j beta 2z L2. We found this to be the generalized reflection coefficient for gamma 1, 2. At this junction, we can define the reflection coefficient. At that junction, we can imagine an incident wave coming in and the reflected wave going back. Since this is time harmonic signal, the reflected wave would include waves that are multiply reflected in the junction in this manner. So this gamma 1, 2 tilde is the generalized reflection coefficient at this junction, including all the multiple reflections from behind the first junction. Okay, so using the same concept, we can say that if we have now say a layered medium where we put in more than one layer, then the wave will bounce back in this manner. And then you can define a generalized reflection coefficient for the 1, 2 interface. Let's say that this is medium 1, 2, and 3. R12 tilde then would be the R12, the local reflection coefficient of first junction, plus R23 tilde e to the minus 2j. I can put in a beta 2z here because the wave number is a number in the z direction. Okay, and then they can say that this thickness here is L2, for instance. And beta 2z is the wave number in that region. So I'm using mathematical parallelism or mathematical homomorphism to write down the solution here. Okay, this is a 3. E to the minus 2j beta 2z L2. Okay, so this is medium 1, 2, and 3. And R2 tilde is a generalized reflection coefficient because I could have multiple reflection coming from behind the 2, 3 interface as well. So the waves from a layered medium can be solved rather easily using this concept. Are there any questions regarding this concept of using mathematical homomorphism or mathematical parallelism to solve the problem of a layered medium by understanding the wave of the transmission line problem? Okay. So if there are no questions, then we will go through doing some ray series interpretations such as this one over here. We can show that if you have a layered medium, if you can write the reflection coefficient like what we have done in the previous slide, you can actually expand this reflection coefficient into a ray series and understand each of the term physically as one of these rays that bounce around like this. So to do this, what we need to do then is to actually take the generalized reflection coefficient and write it as R12 plus R12 tilde. So sorry, this is R23 tilde. Okay, e to the minus 2j beta 2z L2. And then we will have to add and subtract the term in the numerator. The term that we have to add and subtract is actually this term over here, which is R12 tilde, not tilde, R12, R23. Okay, e to the minus 2j beta 2z L2. And I'm going to remove the tildes because I only have 2 layers here, 2 interfaces, so that there's no multiple reflection beyond region 3. And because I have to add this, I have to subtract it out to make it equal to before. Because I've subtracted out. I will have something like this. So this is my numerator. Denominator remains the same. It will be the same as before, 1 plus R12, R23, e to the minus 2j beta 2z L2. Remember that I removed my tilde because I don't have a reflection from this layer anymore in this picture. So the R23 tilde goes away, and these are the entire numerator. And I'm going to do some regrouping. I'm going to do some regrouping because I see that this term has an R12. I'm going to regroup it with the first term. I'm sorry, I should have a square here. Okay, I should have a square here because I have the square that I have added in. and then I should have it regrouped with the first thing. And then, so if I put this together with the first term, okay, what I have then is the fact that the first two terms, the first term and this term that I have added in can be written as R12, 1 plus R12, R23, e to the minus 2j, beta 2zl2, okay? And then what is left behind is what I have as, I don't know if you can see that it will be 1 minus R12 square, R23, e to the minus 2j, beta 2zl2, divided by the denominator. Can you see it? Okay, what I have done is actually group this term together with this term and factor out the R23 e to the minus 2j beta 2zl2 and put it on the outside. And what I have left is just 1 minus R12. And if I do this, then I notice that things somewhat simplifies because, let me see, you can move this further down, that this term in the denominator will cancel this term, okay? And I would have just R12 for the first term. And then for the second term, I'm going to write, I'm going to use the fact that this can be factorized. 1 minus R12 square can be written as 1 plus R12 times 1 minus R12. Okay. And I also use the fact that if you look at the Fresnel reflection coefficient, I can write this as T12. Okay. But this is actually minus R21. Okay, I can use the property of Fresnel reflection coefficient if you go back and look at them again. If you have R12, it turns out to be that. If you were to swap the two indices R21, it would just change the sign and make this into negative R12. Okay, so I can hence change this R12 to negative R21, and then this would just be T21. Okay, so this becomes T21, this becomes T12. And then what I have left is something like T12, T23, 21, sorry, 21, R23, e to the minus 2j, beta 2zl2, divided by the same denominator. Beta 2zl2. Okay, so you have this now, but the next thing you can do is actually to, let me insert the new slide. I have to make this into blank. What I can do next is actually to use the fact that this denominator that I have over there, then anything like 1 over 1 minus x can be written as 1 plus x squared plus x cubed plus x fourth. Okay, something like this can be written as an infinite power series. So I can think of this as something like 1 minus x, and then expand this as a power series. And if I do that, then I will have terms like that. And then I will not go into the details. Okay, I will not go into the details. But then if you go through identifying this power series, is done in the lecture notes, that each of this term can be physically interpreted as such. For instance, if I just look at the first term is just this reflected term. Okay, And if I look at the next term will be this being set to 1. Okay, it would be T12, which is this coefficient here. Okay, and then the wave travels to interface 2, 3 and suffers a reflection coefficient R23, and then it travels another distance. So the total distance traveled by the wave is 2j beta 2z L2. So it gains a phase factor, which is given by this. And then finally, when it emerges again, it becomes this way because it has to go through a T21 over here. So you can taste this ray series one by one. The first ray series will be this, and then you go to the next term, you will trace the next ray series and so on. Okay, so this is the ray series interpretation of the generalized reflection coefficient, which comes in useful in many works. Okay, are there any questions regarding this? So I will not do the substitution, but if you substitute in, you will see this ray series picture coming out. Okay. So sometimes you see echoes coming from a layered medium. What it says is that when you have a layered medium, you don't see a single reflected ray. You will see a single reflected ray from the first interface, and then the second reflected ray from the second interface transmitted again, and then you will have third reflected ray. And this sometimes is called an echo series because it sounds like that the sound wave is reverberating through this layered medium, bouncing back and forth before it reemerges again as another ray. Okay, but this is called a ray series in optics. So let me move on to the next topic then, if you don't have any questions on this ray series interpretation. I'd like to talk about phase velocity and group velocity. And we have learned about phase velocity before, which says that if we have a wave function that looks like this, that is time harmonic, then the wave function can be written like this. Okay, in the time domain, where this is omega, and k and beta are interchangeable in this course. Sometimes we use k, sometimes we use beta. Because beta is used in microwave, k is used in optics, and k is omega over c in optics. And for a particular medium, it's just omega over v, for instance. Beta is also omega over c or omega over v. Okay, in microwave, they are the same thing. And if you look at this wave, and if you rewrite it in such a manner that makes this to become with a k outside. I just factor out the k for the first term. And as I said before, this thing is the phase velocity, and it is something of this form. If we look at this function, it's the function that looks like the phase velocity times t minus z, okay? And we know that a function of this form is a traveling wave. The wave travels in the positive z direction as time progresses, and then it travels with the velocity vp, which is omega over k. And this is called the phase velocity because this is for a monochromatic signal, or wave. And sometimes this would be called CW, constant wave. And it's also called time harmonic. So all this means the same thing. Okay. However, if the medium is such that k K is not a constant, say K is a function of omega. Or maybe I should say that K is not that simple, that epsilon is a function of omega. Then we know that V is 1 over mu epsilon. And then V will be a function of omega. Okay, V is not a constant anymore. So different frequencies will have different phase velocity. And so if you send in a multi-frequency pulse, different frequency components of the pulse would propagate with different phase velocity. And you have to define something that is different now, called the group velocity, because if I have a, for instance, a signal that looks like this, for instance, this signal has to be constituted from different Fourier components because it is not a monochromatic signal. So you can think of this signal as being some of different frequency components by Fourier's theorem, okay? So a non-monochromatic signal can be thought of as a sum of different monochromatic signals. But the bizarre thing is that different frequencies would have different phase velocity because the phase velocity is omega over V. Sorry, the phase velocity is given by omega, sorry. The phase velocity will be given by this equation over here. And you can see that because epsilon is a function of frequency, different frequency components would propagate with different phase velocity. And what happens is that the phase velocity difference makes the pulse get distorted as it propagates. So in the beginning, it might look something like this, but after a while, the pulse might get spread out. And because the phase velocities are different for frequency that are different, there has to be something called the group velocity, which actually represents the traveling of the envelope of this function. So in order to define a group velocity, we have to use a different concept. Let's look at a pulse that looks something like this. Okay, a pulse that looks something like this. It cannot be monochromatic. It actually is a Gaussian pulse. If you were to do the Fourier transform of this pulse, you will find that it consists of very many different frequency components. And in order to describe this pulse, you will have to use a different strategy. So let's talk about group velocity now. That a wave can now be thought of as the sum of different frequency components. Okay, and this V tilde, for instance, could be the solution to this equation, which also follows from your transmission line equation. Okay, we have seen that for transmission line theory, we have the fact that d square, dz square, v tilde z omega is something like plus omega square LC bz omega is equal to 0. What happens if the medium is dispersive so that the capacitance and the inductance are both functions of frequency. So what you have here is that this can be omega square, L can be dispersive, and then C can be dispersive. Then this function here will look rather complicated. So this equation can be the Helmholtz equation that follows from transmission line theory, where both the inductor and the capacitor are frequency dispersive. Okay, in that case, then how would a signal propagate on this thing? So to analyze the signal propagation, we assume that VZT from transmission line theory, we can solve this Helmholtz wave equation. You will still get the fact that the wave, right traveling wave, will be something of this form. Okay, you can actually solve this equation quite easily and show that this is one possible solution. Of course, you can have a left traveling wave also, but let's just keep the right traveling wave. And now look at VZT for this right traveling wave on the transmission line. Let's call it V naught. Okay, let's call this V naught in front, and V naught could be a function of frequency, e to the j omega t minus j kz. Okay, so this could be a signal on the transmission line now, where the k is not that simple anymore, but a very complicated function of omega. In order to analyze this wave, the best is actually to make an approximation of the integrand. And we assume that we have a narrow band signal. Assume that the signal is narrow band as this one over here. So V0 omega only has Fourier components centered around the frequency omega, omega naught. Okay, so because V naught omega is narrow band, it only has Fourier components centered about omega naught, then we can actually say that we can approximate the integrand with something that is actually simpler, saying that, well, let me see if I have it here. It turns out that I don't know if you know this in signal processing, that if V0 omega looks something like this, narrow band, that it has to have something like this too, which is its conjugate image. Okay, so this is omega naught, this is minus omega naught. There has to be an image term at the minus omega naught frequency in order for this to be real value. Otherwise, this thing cannot be real valued. In order for this to be real, on the left-hand side, signal processing says that V0 of omega has to have a conjugate image like this. Okay, and furthermore, you can actually write this as a something like a 0 to, I guess you can fold this. I can carefully fold this for you. You can write this as minus omega infinity to 0, the omega, and then V0 omega e to the j omega t minus kz. And then you can do the other term, which is 0 to infinity d omega V0 omega e to the j omega t minus kz. Okay, and the two of them have to add up to be real value because the left-hand side is real value. And you can flip the integration of the first one to be from 0 to infinity by a change of variable. Okay, you can just do this change of variable, and then the integration range will flip, and then you will have something like V0 of minus omega prime, and then you will have something like J minus omega prime t, and then K of omega prime with a minus sign there, okay, plus this other term. And in order for the function to be a real value, these two terms have to be the complex conjugate of each other. You can prove that by signal processing. Otherwise, the left-hand side would not be a real value. So since they are the complex conjugate of each other, you can actually write this as the real part of an integral going from 0 to infinity, d omega, v naught of omega. Okay, this one actually will become b0 conjugate of omega prime. You can show that in order for the function to be a real value. So finally, you will have something that looks like this, e to the j omega t minus kz. You can just integrate over the positive frequency part. And because the sum of the two components have to be real, you just need to integrate one of them and arrive at this equation. And then now you can know that you only need to integrate from 0 to infinity, but because the signal is narrow band, you need to integrate over a small bandwidth. Okay, so this is 2, so it will be omega naught minus delta, omega naught plus delta. If I call this omega naught plus delta, this part omega naught minus delta, I only need to integrate over this very small region. Okay, and my k is supposed to take values only in that very small region, and hence I can approximate my k. Let me write my omega properly. Okay, I can approximate my k value. Okay, I can do an approximation that since k is going to be approximated only in the vicinity of omega naught, I can say that this is approximately equal to k of omega naught by Taylor series expansion plus omega minus omega naught dk omega naught d omega plus the higher order term. Are there any questions? Okay. You can write down the Taylor series expansion for this plus the other terms. And I will only keep two terms in my Taylor series expansion and plug it in this integral again. And if I do that, then my v of zt will become something like 2 times the real part of I don't know, I wouldn't go through the detail, but if you plug this in, this first term is independent of frequency. Is independent of frequency, so I can take it outside the integral. Okay, and then by doing a nice trick, I also take out another term outside the integral, which is also independent of frequency. So the first term is independent of frequency. I'm going to put in another term that is also independent of frequency and put it back into the integrand. Then the integrand will look something like this, that it will be b0 omega e to the plus j omega minus omega naught t. And then the second term in the exponent is e to the minus j omega omega naught dk d omega t. I don't know if you can see this. I did a number of tricks here. The first thing is to take this outside the integral, so it becomes something like this. And then I'm also going to take this outside the integral and then put it back in. That's what happens here. This is a constant term independent of frequency that I put outside the integral and then put it back in. And then I keep this term and put it inside the exponent. And that will give rise to the last term here. Okay, I hope we can follow all the algebra. But if you look at this thing here, this is an integral. This integral supposedly is going to go from 0 to infinity. And it is rather complicated, okay? And if you look at this part, it actually is a function of t. If you factor out the time dependence, minus dk d omega z. Okay, so I have an error here. This would be a z dependence because I plug in k with this Taylor series expansion, and there should be a z dependence. And this would be a function of t minus dk d omega z. But I'm only summing over very little Fourier components in the vicinity of omega naught. So since this has very few Fourier components in the vicinity of omega naught, this is like a Fourier transform. You see that this is like a Fourier transform, but collecting frequency very close to omega naught, which means that this has to be a slowly varying function. Okay, so this has to be a very slowly varying function. But this thing outside remains rapidly varying. Okay, so what you have here is that this is slow, this is rapid. And if you take this slow function, multiply by the rapid function, and then take the real part, then you would have this looking like this. Okay, so f is the envelope function. The envelope would travel with the velocity called the group velocity, and that velocity is dk d omega. The rest of the thing, the inside inert of this wave function, travels with this velocity, and that is called the phase velocity. Okay, you look at this, and you look at this part here is traveling with the phase velocity. Okay, so you can see that when you have a broadband pulse, like what we have here, okay, then it is not extremely broadband, but narrow band enough so that you can do this Taylor series approximation. You have a wave that travels with its inerts at the phase velocity, but the envelope is traveling at the group velocity. Are there any questions regarding this? So this is a more mathematical analysis of the group velocity and the phase velocity that you might not have learned in your undergraduate days. In the undergraduate days, you would just beat two wave functions together and find out that the phase velocity is one and then the group velocity is another one. Okay. If not, I'd like to go on to the next topic, which is wave guidance in the layered medium, or the transverse resonance condition. What we have seen is that the generalized reflection coefficient is equal to R12 plus R23 tilde e to the minus 2j beta 2z L2, or 1 plus R12 R23 e to the minus 2j beta 2z L2. How do we know that when we have this medium, okay, let's call this R23 tilde, that if you send in the wave here, R12 tilde is this generalized reflection coefficient. How do we know when we have a guided mode in this layered medium? We know when we have a guided mode when R12 tends to infinity. When R12 tends to infinity, just like the surface plasmon case, remember, we just look at the one interface reflection coefficient. We look at that, we found that at a certain frequency and certain combination of parameters, the reflection coefficient becomes infinite. And when that happens, it indicates some resonance phenomenon. The same thing happens. And if we can find the reason for R12 tilde going to infinity, it means that you need no incident wave, and yet there will be a reflected wave. And that means that there's a wave here that can sustain itself. Okay, a wave here that can sustain itself without incident wave. This would be zero. Okay, the incident wave would be zero. And yet there is a wave bouncing around, giving rise to a reflected signal. That is what it means when this thing is infinite in value. It says that you need no incident wave to generate the reflected wave. And we saw this in the plasma resonance condition. Okay, this would also happen inside the layered medium. It happens when this is equal to 0. This is given the name, it's called the transverse resonance condition. Okay, it's called the transverse resonance condition. It is a condition that will make the denominator goes to 0, which makes this become infinite in value. And when that happens, you would have wave guidance. That means the wave can sustain itself without an incident wave from the outside. Okay. And you can also study the transverse resonance condition using this picture over here. So what I have is that if I look at the transverse resonance condition, what it says is that the wave, okay, can also be written. This is one way to write the transverse resonance condition. Okay, this is one way to write the transverse resonance condition. You can also give it physical interpretation because you know that this is just minus R21. So it can be written as 1 minus R21, R23 tilde e to the minus 2j L2 is equal to 0. And you can also say that this has a physical meaning at 1 equals R21. Maybe we can just make R23 without a tilde for better physical understanding. Okay. It says that when this happens, you have resonance. And you can see that this is the case where I think of this region 1, region 2, region 3, that I have a wave starting out with 1. Okay, the wave starting out with 1. Okay, and then the first time it bounces off, it will bounce off with the reflection coefficient of R21. And then it travels, there should be a factor of 2 here. It travels a distance of e to the minus j beta 2z L2. Okay, L2 is the length of this thing. It will gain the phase of that. And then the next time around, it will bounce off at this point. It becomes R23 e to the minus 2j beta 2zL2, sorry, just 1j, okay? It bounces off once with the reflection coefficient R23, but then R21 should be also included here because then the amplitude of the wave at this point should be R21, R23, but with the accumulated phase to be here. And then this wave goes back to its original place. Okay, by the time it reaches over here, the amplitude of the wave should be R21, R23, because it travels these things 2 times, so the phase should be 2j beta 2z L2. And in order for guidance to occur, which means that in order for constructive interference to occur, this wave must be identical to the wave that is coming in. So this must be equal to 1. Okay. So transverse resonance condition says that when the wave, after having bounced 2 times, after having traversed the distance of 2j beta L2, the wave becomes itself. And when that happens, we have resonance. Okay, we can have guidance or resonance, and in that case, you don't need energy to sustain this wave bounce back and forth. You can also understand that by using this picture over here. Are there any questions regarding this transverse resonance condition?
Professor,
Yes, sure.
does this mean
Yes,
that
ask a question.
there will be no energy loss?
There will be no energy loss if the medium is lossless. Okay, if the medium is lossless, and that's a very good question. You might think that, well, how come the wave can bounce around with no energy loss? And that would happen only if there is total internal reflection at both interfaces. The wave bounces around and there will be no loss. Okay. However, if the reflection here is not total internal reflection, there will be some energy loss, and you would not have wave guidance. Wave guidance for dielectric interface can happen only when you have total internal reflection at the 2 interfaces. Okay. So if there is the case, if you have total internal reflection, then you have guidance, and the guidance condition can be found by using this transverse resonance condition. There will be no energy loss if the medium is lossless. However, if the medium is lossy as the wave bounces around, it will be dissipated as well. Okay, that's a good question, because I never explained the fact that why this wave is guided. Okay, this wave is guided because of multiple bounces due to total internal reflection. That is how a wave is being guided on the dielectric slat waveguide that we will learn in the next lecture. The dielectric slat waveguide is not as cool as the surface plasmon polariton. You see that in the surface plasmon polariton, you don't need double bounces. You just need one interface. Okay, and you can trap a mode at that interface. But other than that, most of the time you need 2 interfaces to trap a mode in dielectric waveguide. Are there any questions? If not, then I'll let you go. Thanks for asking a good question. Who was the one who asked the question, please?
It's Nahian.
Oh, Nahin. Okay, good. Thank you, Nahin. Okay, I'll let you go then. Okay, see you on Wednesday. Hope everything goes well.